About our final piece of new content in this lesson, comparing two means. So this is going to be doing inference for two samples, computing the mean in each sample, and you're trying to compare two population means one to the other. So that basically comes out to mu1 versus mu2, or the difference between them, and we'll talk about why. Sample T procedures. And this is different than the example I went over in the last set of notes, which was paired T procedures. That may look like two samples, but it's not two samples because every piece of data, individual piece of data, is paired with another, and you actually combine them before you do the inference. Okay, so something that we are used to at this point: shape, center, and spread of the sampling distribution. When I choose a simple random sample of size n1 from population 1, and it has mean mu1 and standard deviation sigma 1, and then we do the same thing from a second population. The sample sizes don't have to be the same necessarily. So here's the shape, center, and spread of the sampling distribution of x1 bar minus x2 bar. It'll be approximately normal as long as sample sizes are large enough, and checking that both sample sizes are at least 30. Or as long as the samples, if you don't have that information, you can graph the samples, and as long as there's no extreme skew, we'll be safe to use T procedures. The center, it'll center over mu1 minus mu2, the difference in the population means. And then standard deviation is this formula. Here's the deal though, for this last section, we're not even going to do really any of this by hand. We're going to be pretty reliant on the calculator because these computations get kind of messy. So, all right, there's a visual of what we just said. mu1 minus mu2, standard deviation, normal, as long as the large count condition is satisfied. Okay, so it is going to be a T distribution. So sorry, I misspoke over there. Not necessarily roughly normal. T distribution looks similar to normal, but we know has heavier tails. All right, so the conditions, the things you have to check. This is random. You have to make a statement that the data come from a random sample or randomly designed experiment. 10%, so for each sample, it has to be less than a tenth of the population, or another way of saying that is 10 times the sample has to be less than the population. And then large counts, either both are 30, both sample sizes are at least 30. If you know both are already normal, their parent populations are normal. If not, if neither of those is satisfied, is graph to assess the normality of the population. And so you're just gonna usually do a box plot for each, and as long as the box plot doesn't show extreme skew, we're gonna say it's gonna be safe to use T procedures. All right. That's the formula for a confidence interval. Again, we're going to be using our calculator for the most part, so I'm not going to worry too much about this. All right. We won't use pooled two sample T procedures. That's just a setting in the calculator that we'll make sure is not selected. Okay, so here we go. Let's do our first example. After buying many helium balloons, only to see them deflate within a couple of days, Aaron and Jenna decided to test if helium-filled balloons deflate faster than air-filled balloons. To find out, they bought 60 balloons and randomly divided them into piles of 30. Again, that's very important. So this is a randomized experiment. Oh, okay. So into two piles of 30 filling balloons, in the first pile with helium and the second pile with air. Then they measured the circumference of each balloon immediately after being filled, and again 3 days later. The average decrease in circumference of the helium-filled balloon was 26.5 centimeters with a standard deviation of 1.92 centimeters, and the average decrease of the air-filled balloons was 2.1 centimeters with a standard deviation of 2.79 centimeters. So right off the bat, 26.5 centimeter decrease in the circumference of helium balloons versus only 2.1 centimeter decrease with air. These data provide convincing evidence that the helium-filled balloons deflate faster than air-filled balloons. All right, so they're asking us to conduct a significance test. So I'm going to come over here. We're going to get started on state, plan, do, conclude. So, all right, state. We want to conduct a sample test for mu H, so helium minus A. And then I'm going to make a statement about what those are. So mu H is amount. Nice way to write this. Let's say a decreased helium. A decreased now let's write our hypotheses. So our null and all our alternative hypotheses. Well, our alternative significantly greater decrease in helium circumference, right? So another way of writing that, if I subtract mu A over, is going to be difference is greater than 0, right? And then that means that our null hypothesis is that equals 0. So this is a one-tailed test for mu H minus mu A. And the other thing I need to do, they didn't specify a significance level. Oh, give me a break. So I'm going to say that alpha, we're going to just set it to the 0.05 level. Now, just going back and looking at this, I mean, there is a large difference between 26.5 centimeters and 2.1 centimeters in terms of the decrease in circumference. So it seems like a significant result, but we still need to kind of do the statistics to check that. All right, so now let's plan. We'll start with random. Say randomly designed experiment in this case. Well, there's not a population really of balloons. They're continually manufactured. So we'll just say balloons are independent. And then large counts. Here I'll just say that my sample size, so NH equals NA, meaning the number of balloons for helium and the number of balloons of air are both 30, which is greater than or equal to 30, so our large counts is satisfied and we don't have to graph each sample separately. All right, so we are finally at the do. And remember, we're going to conduct a two sample t-test for a difference in means, and I already put that up at the top, so I'm just going to actually do the calculations and copy down what we need. Over here. Second. Stat tests rather. What we want is a two sample t-test. In this case, they actually gave us statistics, right? So our first sample mean, I'm going to use this to be my helium data, just because that's what they gave us first, was 26.5 centimeter decrease with a standard deviation of 1.92 centimeters. Sample size was 30. Second mean decrease in circumference was 2.1 with a standard deviation of 2.79. Sample size was also 30. And we said that mu1 is greater than mu2, that the helium greater than that. And here's that pulled thing. And as we said, no, don't need to know anything more about that. All right, so you're going to want to copy down most of this. I'm going to copy it down real quick, and then I'll go back to our slide here. Our T critical value, 39.46. P-value that we want to use, but don't negative 40. That means really it's a decimal with 39 zeros in front of it. So I'm going to say P is approximately 0. Degrees of freedom. To calculate degrees of freedom in a two sample t-test is a little bit more complicated. So your calculator will do that calculation for you. You just need to copy it down and take it to a couple decimal places. So degrees of freedom, about 51 point. The rest of this, right? We got all the important stuff. So let's get back to now that we have all that information here. P-value, which means it's really unlikely that we would get our result by random chance. So what we're going to conclude is we're going to say evidence reject null in favor of HA. Whoops. We have convincing evidence that helium leaks faster than air. So interpret the p-value that you got in part A of this study. So we just want to be really specific. That's a conditional probability, right? So all we're going to say, the probability that we get difference as large or larger than the one we got, which was what? Geez, it was 26.5 minus 2.1, so 26.5 minus 2.1 is 24.4. The true difference is 0. Remember, that's our assumption in the null hypothesis. Is about a 0% chance that we would get a sample difference that large or larger if the true difference is 0. All right.